Assalamu alaikum. In today's video, we're going to be talking about the circular motion on the surface of the earth. That is, if a body is moving either through a full circle or even a part of a circle, but is doing so on the surface of the earth. We are going to be taking in consideration what affects that motion, how to derive and use the mathematical formulas that govern this motion, and how do cars, bicycles, motorbikes physically maintain a circular motion while moving on the surface of the earth, whether they are doing a turn or they are going through a circular path. And that is going to include talking about banking of roads and tilting for the bikers, and when you see the bikers doing a tilt when they are doing a turn or going through a circular path, that is also going to be included in today's video. And we are going to start so by taking in consideration a term that we already know from the general circular motion, and that term is centripetal force. Now, we already know that if there is a body that is moving through a circular motion, it has to have a centripetal force. This force exists for all kinds of circular motion. Centripetal. And in the simplest example of a circular motion, we take a mass that is tied by a string and then taken around the circle. Like if there is a kid here and this is a string and is doing this, taking the mass around a circle, the centripetal force is actually the tension on the string. But when we are talking about a car or a motorbike or a bike that is doing a turn or going around a circular path, there are no strings here. There are no strings attached here. So from where does the centripetal force originate here? Well, first of all, let's establish that the centripetal force is between the body itself and the center of the circle, or the center of the circle that this arc is part of. And let's denote this force by F, capital F. If this is the surface of the earth here, we can draw a free body diagram. This is a bike. The bike is going to have two opposing forces. One of them is the weight of the bike itself, that is generated from gravity. So weight, which equals mass multiplied by the acceleration of the Earth's gravity. The force that opposes it is the normal force, as explained by the third Newton law, or Newton's third law. For every force, for every action, there is a reaction that is opposing in direction and equal in amount. So this is going to be the normal force, opposing in direction and equal in amount or in magnitude. Now, if this bike is doing a turn towards the right side, the right hand side, then it's doing a circular motion that has a center on the right here. So there is going to be a centripetal force on this direction. This force is generated uh, due to the friction between the surface of the earth and the tires of the bicycle itself. And this is also emerging from Newton's third law, because there has to be a force. This is an action. There has to be a reaction. There has to be a force that is opposing in direction, which is the friction force. However, this friction force is not equal to the centripetal force, especially if the bike is going in a high speed, because the faster you go, the more centripetal force you have, because the centripetal force is proportional to the velocity. We know that because the centripetal force equals the mass multiplied by the velocity squared divided by the radius of the central force, or the circle on which the body is moving. So the centripetal force is proportional to the squared velocity, and that cannot be maintained by the friction alone. So what happens here is the bike itself is going to simply topple. They're not going to be able to maintain the circular path. They're either going to topple, or they just have to go through a straight line. But what happens naturally is that the biker is going to tilt. And if we draw another free body diagram here, and we take again the weight of the bike itself, the biker is not going to be straight like this. It's going to actually tilt. This tilting is the factor that is going to maintain the centripetal force. So we have here the centripetal force, and now the normal force is not going to be like this. It's not going to be straight up. It's not going to be direction straightly opposing the weight, because the normal force is always against the surface. And since the body is pressing against the surface this way, the normal force is going to be this way, opposing in direction. If you are leaning against a wall, this is the wall, and you are leaning like this against the wall, forgive my horrible drawing, you're going to have a normal force on this direction because you are leaning on this direction. The friction is still on this on the left direction, but we are going to ignore friction because it's negligible. And this tilting or banking is going to be enough to maintain a circular path. Now from here we can take complete this right triangle here with a line that is parallel to the centripetal force. So this is going to be F, and this is going to be mg because it's straight along the weight of the body. And we're going to have an angle here that is theta. We can see that sine theta equals F divided by N. The hypotenuse is N, and the opposing is F. Cosine theta is mg over n, and tan theta equals F over mg. And from this tan theta here, we can deduce that the centripetal force F is going to equal mg multiplied by tan theta. So the centripetal force equals the weight of the body multiplied by the tangent of the banking angle or the tilting angle. And this angle is the angle between the normal force and the vertical, or between the body itself, the tilting of the body itself, and the vertical. And the unit is newtons. The unit for force is Newton. Now, from general circular motion, we know that centripetal force is the mass multiplied by the velocity squared divided by the radius. So if we combine this law with this formula with this formula, we'll find that mv squared divided by r equals mg by tan theta, and we can solve for v squared equals multiply both sides by r over m, m divided by m equals 1. So v squared equals r multiplied by g multiplied by tan theta, and so the velocity is equal rg tan theta. And the unit is meters per second. So we can see from here that there is a relation between the velocity and the centripetal force, and that for both of them, they both take upon consideration the angle of the banking. So what does this mean? This means that the velocity is very important when talking about circular motion on the surface of the earth. If the velocity is too high, then the centripetal force is too high, then it's going to be more difficult to maintain a circular path. And since the circular path is maintained through the angle theta, so for higher velocities, we're going to require more banking because they are all proportional to each other. F here is proportional to tan theta, and F is proportional to the velocity squared, and the velocity is proportional to the square root of tan theta. So they are all proportional, which means that for higher velocities, we're going to have higher centripetal forces, so we are going to need more banking in order to maintain a circular path. While F is inversely proportional to the radius. So if the radius is less, F becomes more. So if you're taking a longer turn, you're going to need less force than the force you're going to need if you're taking a shorter turn. And all that is going to be reflected on the angle theta, or the banking angle. That's why when you are riding a bicycle, when you are riding a motorbike, when you're doing turns, you have to tilt a bit so you can maintain that turn. While when you see motor racers, their banking angle is very steep. They bank really dramatically. Why? Because they move in high velocities. While you're moving in a relatively lower magnitude of velocity, so you do not need a big angle for banking, while they need a really big angle for banking because they're moving in high speeds. Same way, you can notice that in highways there is a banking of the road itself. You will find that the car, and again, excuse my horrible drawing, the road itself is banked so that the cars can maintain a turn or a circular path. The faster the car is going, the more banking you need for the road. The faster the car is going, the more banking you need for the road. If the road was not banked, you will find out the centripetal force is too strong to be maintained by the friction, and the car is going to topple on the other direction. On the other hand, if the car is not moving fast enough, if it's not going fast enough and the road is already banked, the car is not moving fast enough, you will find that the car is drifting towards the center, because you need to have a balance between the velocity of the car, or the speed of the car, and the centripetal force. And all of this is governed by those two rules. You have here one formula to find the centripetal force, and another formula to find the velocity that is needed to maintain the circular path. Now, let's take some examples. A car of mass 1 ton, or let's just say 10 to the power of 3 kilograms. We're taking maths, not weight. Moving at 72 kilometers per hour in a circular road, in a circular path. With a radius 100 meters, with a banking angle tan inverse 0.15, and let's take G as 10 meters per second squared. Now here the banking angle, we already have tan theta equals 0.15, because we have tan inverse, so we don't have the angle itself, we have the tangent of the angle, which equals 0.15. So tan theta equals 0.15. The mass equals 10 to the point of 3 kilograms, and I usually write the the given measurables. I write them down so it's easier to follow and less likely to make mistakes. The velocity is 72 kilometers per hour. We need to convert this to SI units. So the SI unit for velocity is meters per second, not kilometers per hour. So in order to convert, we have kilometers multiplied, so I'm going to put it as divided, and we have hour divided, so I'm going to put it as multiplied. And 1 kilometer has 10 to the power of 3 meters, and 1 hour has 3,600 seconds. Kilometers, hours. So the velocity equals, this method is the method I use to convert, which I believe, at least for myself, it's better, or it just makes me less vulnerable to making mistakes. Okay, so 72 by 10 to the 3, so it's basically 720 divided by 36, and this equals 20 meters per second. Now let's find the centripetal force. F equals mg tan theta, which equals 10 to the power of 3 multiplied by g, which is 10, multiplied by tan theta, and this equals 1500 newtons. Now let's see if this velocity, the velocity that the car is moving at, is suitable for this road with this banking angle. We can do so by calculating the suitable velocity, which is v equals square root of r g tan theta, which equals square root of r is, we forgot to write r is 100 meters, so 100 multiplied by 10 multiplied by 0.15, which equals square root of 150 meters per second. Now this here, square root of 150 meters per second, this is the suitable velocity. So what we need to do now is to compare between the velocity that the car is already moving at and the suitable velocity. Now, an easy way to compare this, because square root of 150 is not an easy number to imagine, you can do is square this number, so it's 400. So the velocity at which the car is moving is square root of 400, which is 20, and the suitable velocity is square root of 150, and you can see that this is higher than this. So the velocity at which the car is already moving is higher than the suitable velocity. So this velocity is not suitable for the road. It's too high. That means the car will not be able to maintain this circular path, and it's going to top. And that is it for the circular motion on the surface of the earth. This lesson is made and prepared for the Sudanese secondary certificate students from their curriculum. I hope that the lesson is clear, and I am going to be posting another video with some other examples and solutions, and I will see you on the next video. Thank you.